let's just go. So this is digital systems, and we have been taught this Mano machine thing, right? They never mention it's actually called Mano machine, but it is called that. It's actually very popular. I don't know why people use this particular thing so much, but never mind. Let's just get started. uh, so the machine works like this. So you just have, first of all, I'm just gonna draw the structure of this machine. So you have a common bus system. It has multiplexers which take in input S0, S1, S2. I should probably draw it cleaner, right? So just a square, another rectangle, not this, I want a rectangle. I don't think it understands what a rectangle is. Yes, it actually does not. Never mind all that, I'm just gonna do this. Yeah, so this will be our bus basically. Okay, not like this. I don't think it, okay, yeah, that's how it works. So this is our bus. uh, so it takes in multiplexers, S0, S1, S2. And so the way this works is that you have a bunch of registers, which are trying to put something on the bus, but you can't have all of them putting the same thing on the bus. I mean, all of them being connected, like by putting stuff on the bus, because that would cause a short circuit. So the very sort of primitive way of doing this would be using tri-state buffers, which are basically like devices, which are basically just buffers. You have an enable port, and so whenever the enable port is off, we call it a Z, that is a high impedance state, as in there's nothing, no current, no voltage, nothing connected to this wire. You can imagine as if the wire is just hanging in the air, right? So as if the wire is non-existent, you have removed it from the circuit. That's a high impedance state. Anyway, so we won't be using that like in proper professional circuits. So we just have this multiplexer sort of thing. So let's just start drawing the elements. First of all, you have a memory. Yes, a big memory of 4096, which is, by the way, like 2 power 12. So this is 2 power 12 times, so each word will be 16 bits, right? So 16-bit numbers, 409, or registers, 4096 of them. Cool. So I'm just going to call this element as M. This element has so 2 control signals. So it has a write and a read. It has this other input, which is the data bus. It's called the data bus. So so we'll just be putting 12 bits inside of it. All right, and this is coming from another register. All right. So this is called AR, for address register. Below that you have this thing called the program counter, which I'll explain in a bit. So if any of you have like ever done this thing called assembly level programming, you would be familiar with what a program counter is, what a stack is, what the memory actually is, and all that. All right. Then you have, so after the program counter you have this data register, right? I think I'm drawing it correctly. I kind of don't remember. I think it was an instruction register, not, yeah, that must have been the thing. Was it the instruction register? I actually don't remember, but never mind that. So I'm just gonna draw the instruction register directly, and then you have the data register. I think that's how it's supposed to be. No, wait, okay, this is wrong. You don't have the instruction register right there. You actually have the data register, right? And then you have the accumulator. Then you have the instruction register. Oh, first you also have the input and output stuff. So you have this thing called INPR, which is a smaller register. So whatever like input device you have connected to this machine, it's gonna send its signal to this register, and then that stuff is gonna go to the accumulator depending on the working of the program. You also have the output register somewhere over there. It's also connected to the bus, and yeah, so it also kind of sends the signals, doesn't it? Yeah, so I should also consider that. I think it was just about the accumulator. If I'm I think, yeah. So each of them are connected to the bus like this, and so I'm just drawing one wire for this, but it really is just like, so this guy is actually like 12 wires, and so it's connected to the LSB of the bus wires. I mean the lower bits of the bus wires. This is the program counter is also 12, the register is 16, this register is I think 8. Yeah. uh, the INPR register is not connected, like it cannot send to the bus, but yeah, okay, I mean it cannot send to the bus, that's pretty much the thing, but it is connected to the accumulator through some weird thing. I'll show that later. The accumulator obviously can send to the thing, and it has 16 bits. Okay, then you have the instruction register, which is also 16 bits, and it can certainly send to the thing. Right, and then you have the temporary register, right, and that also has 16 bits. I think so. Did I miss something? I don't think. This is probably all of it. So how many elements do we have? We have S0, S1, S2. I think this was till 8, right? So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. Oh no, wait. Okay, so this guy doesn't send anything. So yeah, makes sense. Right, so that's exactly. Oh, this also has to send, obviously. So this will be 16 bits once again, right? So this is just the address bus, sorry, and this will be the data bus basically, as in the data is coming to our stuff, basically the main hardware from the memory through this bus. Yeah, okay, cool. I'm gonna minimize this thing because I need to draw the other part. So once again, all of these wires are connected through multiplexers, well, precisely 16 multiplexers, and then depending on the values of S0, S1, S2, you feed into the bus. Alright, but also you can read from the bus. I'm gonna show that. And so why am I drawing all of this stuff when the diagrams are there? That's just for practice, really. Like, I just want this to be, done correctly in a way. As in, I want to remember all of this, and that's why I'm drawing it again and again. But yeah, copy this, paste. Just gonna copy the bus like that. Cool. Okay, so the thing is, accumulator cannot take from the bus directly, as in it does not have that capability. I guess this will work. Yeah, right. Yeah, so what was I saying? Right, the accumulator cannot take it directly, so instead what you actually do is you have this ALU unit, arithmetic logical unit, come on, like people know it. And so I'm just gonna draw it like a square box, I don't know. ALU. It has some control signals which enable it to do different sort of operations, so like addition and complementation and all sorts of stuff really. So the accumulator can, so okay, first of all you have this thing connected to it, you also have this thing connected to it, the data register, and also the accumulator itself is connected to it. So what this means, so since the accumulator is connected, what this means is that you can do, like, say, the complementation of the bits in the accumulator in just one clock cycle. Oh, I should also draw the clock signals. So yeah, okay, all of these registers, they are in fact dictated by the clock, obviously, right? Except I think this input register is not dictated by the clock. No, it is. It also is, probably. Like, whether or not to send. Is that the thing? I don't remember it exactly. Just to be safe, I had another clock over there. Right. Yeah, okay, that makes sense. So the output register obviously needs a clock, and it needs some control signals as well, so that it can send stuff. uh, this obviously needs a clock. What about this one? Yeah, okay, this makes sense. Cool. And obviously you have a clock signal over there. Okay, cool. Anything I'm missing? No, this looks correct. Alright, so now I'm just gonna double check and see. So see the actual structure, see what's going on. So once again, the memory unit, the AR PCDR. Yes. So the out register is actually not connected. I see. The out register cannot actually send stuff. It's the one that receives stuff. So sorry for that. Yeah, I mean you send stuff to the out register, not the other way around. And so it's actually supposed to be at the bottom. So don't have that over there. So I'm just gonna shift all of this. Alright, so now you have an out register over there, whose whole purpose is to just send stuff to the outside world, basically the output device. And this also has a clock cycle. So okay, apart from that, everything's okay. Yes, input register, you have the input thing, AC thing. Oh, you also have this extras, so this connection obviously, and you also have this extra thing called E. So it's just one bit. It's not a register, in fact it's just a wire, but it's important. Yeah, because a lot of operations are based on that. So yeah, I think I've got the circuit down correctly, 16-bit bus and all of that. Cool. So now I can actually go to the main thing, which is how does this actually work. So you have 25 operations. I'm gonna list them, all of them. Actually, let's not list them directly. I'm gonna first explain the sort of bigger structure. So yeah, okay, this is just in a way just the data path circuit. Like you have all the connections and everything, but none of this is actually connected like to a control circuit. So basically, like, yeah, if you can control it, then you can get stuff moving, but right now it's not moving. So you have this control circuit. I'm gonna call it CU, which basically controls the data path circuit, which is what I've drawn over there. So yeah, you have a memory and all. So I'm just gonna include the memory in this as well. So it sends control signals to the data path, right? Cool. But what goes into the CU? So the stuff that goes to CU is this. One is the instructions that we read, so from the instruction register. So you have the instruction register over there somewhere, I don't know, IR. So the instructions are like this. The first bit is something we call I. So yeah, it has some significance. The next 3 bits are actually what's considered the OP code, or so not okay, the operation basically. So I and this combined, that's actually the operation code. And then this stuff is the address in the cases that we need. It could also be that this whole thing is actually the operation itself, and then this is just some declaration that it is of a certain type, but for the most useful sort of manipulations, this will be the address. So it's 12 bits basically. So it's 12 plus 3 plus 1, that's 16 bits. So that's your instruction register. What happens is that all of these things, sorry, not these things, and that's just the address. That just actually goes into the AR thing eventually once you fetch the instruction and all that. This stuff, so these 3 bits, they go into a decoder, a 3x8 decoder, and that produces these guys, so D0, D1 and all that stuff, right? So that's, so okay, all the way till, I don't know, D7. And so each of them can be 1 only if all of the other ones are 0. That's just the way decoder works. So that's 1 thing that this CU uses. It takes in all of this stuff. It also takes in some other stuff, which is basically something that we call a timing signal. So I'm just gonna draw lines for there, but yeah. So you could be having like as many timing signals that you really need, but for this case, let's just say we're limited to, I don't know, 8 uh, values. So you just have T0, T1, T2, T3, T4, T5, T6. So till T8 basically. Sorry, T7. So this can be generated with, using a 3-bit counter and then putting that into a decoder, right? So you can have a 3x8 thing, and then what was I going to say though? Yeah, and you also have a counter. So this is called the state counter or the sequence counter or whatever. It obviously needs a clock, and then you send stuff over there. So it starts off at 0, and then it just is incrementing unless you clear it. So clear is another signal that the control unit generates, and yeah, actually that's pretty much the thing. Yeah, I'm just gonna verify that as well. Just wait a second. Okay, this was actually the start of the chapter. Right. Oh, so actually we have a 4-bit sequence counter, not a 3-bit sequence counter. So this will be a 4x8 decoder, and this is actually like 4-bit, and so this will be like all the way till T15. So you can have 15 timing signals. Yeah, that's the way it works. I think, yeah. So T7 is actually the last thing that you will probably ever need, but it's okay, I guess. 16 is not bad. Like, it's just an overkill, but who cares? Maybe you will define your new sequences and like new instructions, and then stuff gets messed up. Who knows? But yeah, so that's the way this thing works. So what is all of this? What does it actually do? So what happens is that inside of the memory, right? So you have this AR thing, right, which goes into the M, and so you have these memory bits coming off. So what's going to happen is that this stuff has to be put inside the instruction register, right? So this is actually part of the data path, like somewhere over there. I don't know, it's somewhere. Yeah. So this stuff, this value, this has to be put in the instruction register, and then this instruction register is decoded and understood by the computer, or so yeah, it's like this address, whatever this thing is, it's then sent to the AR register, and then stuff happens with it. And so you have this thing called program counter, which basically tells us the address of the instructions in our memory. And so whatever is in the program counter, you first move that to the AR thing, and then whatever is the the actual value in that address, you put that into the instruction register. So it works like this. So at T0, so remember you have this state counter thing. So the first thing that happens is you reach state T0. So at T0, what happens is whatever is in your program counter, put that into the array, into the AR register. All right. Yeah, and then you can kind of increment the program counter, because you'll never actually reread this thing. You have to read the next instruction later on. So you can increment the program counter, and I'm just gonna call it PC++. So by the way, most of these actually have the increment, load, clear, all 3 control signals, except this stuff. So this obviously does not have anything. Like, it just has, so it doesn't have a load signal, it doesn't have a clear signal, it doesn't have an increment signal, obviously. This on the other hand, it only has a load signal, because it can load from the bus. So it has an LD for load, everything, and also the instruction register, it only has the LD thing. Yeah, I mean, this wouldn't make sense. Like, you got an instruction, and then you change the instruction, and then you do this thing. It doesn't make sense. So it only has a load thing. It doesn't have a clear, because obviously you don't want to be modifying stuff. All right. Everything else has all three signals. They have the load, the increment, and the clear, right? uh, that will come in handy. Well, okay. What was I going to do? Right, so at t0 this stuff happens, and at t1, so it's now that your program counter is at the next thing. All right, and inside of your AR register you have the address of the instruction. So whatever is the instruction itself, you want to put that into the instruction register. All right, yeah. And at t2, so this, I told you, right, that this instruction is connected to decoders and stuff. So you will have all these d0 to d7 values. At the same time, you also have this address which you will be using later, so you have to store that address somewhere. And so we just do this thing. So everything from so all the like first 12 least significant bits basically, so 0 till 12, or okay, in Verilog style this would be like 11 down to 0, right? Yeah, okay, this makes sense. So this is the stuff that happens every time you run an instruction. So like this processor thing, it just keeps doing this over and over and over again. But this is not the only stuff that happens in t3. You do some things which are related to the operation that this is trying to do when it reads this instruction that is stored in the IR right now. So for each instruction you can have multiple clock cycles, and it does some sequence of things, micro operations they call it, that does whatever operation you want to do, right? And so you can program your computer this way. Basically you can put a bunch of instructions. So you have this memory, right? And so you just put bunch of instructions over there, and then you can put a bunch of data. And so depending on this instruction, so your computer will read this instruction, right? So the program counter is initially at this thing, then it will be like program counter is 1, and so on. So it just one by one starts reading this stuff, and then the instruction goes to the instruction register. It decodes it, it does whatever it has to. Sometimes it uses the data, sometimes it doesn't, sometimes it just deals with the register. That's called a register reference instruction, which only deals with the register. If it deals with the memory, it's called an MR yes, a memory reference instruction, which actually has two types. So it's a direct MRI or an indirect MRI. So an indirect, actually I'll explain that later on. Cool. So far we have talked about this stuff essentially. I also want to sort of talk about this thing called an interrupt. So an interrupt is something that is, so you have some device that is, how do I even say this thing? Yeah, okay, this is actually kind of weird. Okay. I should actually first explain the input output model so that you can understand this. So you have this input device, and then you have some interface, and from that you are reading stuff, right? So from that you are going to the INPR register. So this stuff, the communication between this interface and the INPR thing, that happens serially. So I shouldn't be drawing it like this. Instead I should be drawing it like this. And then from here you can go to the accumulator. It's like in a way connected to it through the bus. Actually it is connected directly, but whatever. Yeah. And then from there you can go to the bus, and from there you can go to the output register. Basically not just the bus, but like do whatever you want to do, you have to do whatever process you are running, then to the output register. Once again there's some interface, and then you have the output device. Alright, so that's like a simple thing that happens. Take input, do some processing, right? So instead of bus, I'm just going to call it process or something. So whatever operation you have, then you do all of this, and then you like get some output. That's the way it works. But it also has some flags, that is some signals which tell us whether or not the input device has given you the input or not. So you have this flag called, I'm just gonna call it flag input, or FG input in fact, and you have this flag FG output. So what happens is whenever an input is read from the device, this FGI thing goes 0. It goes 1. That is to say that the computer is being told that yes, you can read from it, you can do whatever you want, because the input has been read just now. Similarly, whenever some data has been transferred to the output device, this FGO becomes 1. That is to say that whatever data you had put into the register, the output register, that has been safely transmitted. Now you can put something else. So whenever it's 1, the computer has to take some action. Otherwise, the computer should not take any action, right? Yeah. So what an interrupt in is basically is that so if any of these inputs, so FGI and FGO are 1, and you are saying that you have enabled interrupt, which is another flag which is called ENI. So if you have enabled the interrupt, yeah, this is actually a flag, and you are in some particular state in which it's not like assume that you don't have interrupts. So in that case, so if enable interrupt at the same time, either FGI or FGO, in that case you say that okay, we can interrupt in the next operation, as in whenever your operation will be like executed, all of the clock cycles are done for that operation. In the next operation you can run something which is predetermined. So inside of memory, what you can do is wherever you are, whatever your program counter is at, you take the address, so whatever is in the program counter, you put that stuff on the 0th location in the memory, and then you have some instructions which are basically run every time that you have this reset. So not reset, you have this what is it called, interrupt thing going on, and then you have this jump statement or branch statement, however you want to call it, that goes to this thing. So it indirectly references this address. So whatever is the address written on this, basically it actually references to that value, and then it sends that value to the program counter, and then program counter comes here, actually not here but like the next thing, but whatever, and then it starts doing stuff again, right? Yeah, so that's like how an interrupt works. So whenever this happens, you do all of this. Not exactly. Whenever this happens, you actually set another another flag R to 1, and when R is 1 and you run the fetch decode thing again. So this, by the way, is called the fetch decode part of the operation. Whenever you run that again, just before that, you should check if R is 1, and if R is 1, in that case you are saying okay, instead of running an instruction cycle, you are going to run an interrupt cycle. So if R is 0, then you do something called an instruction cycle. If it's 1, then you do an interrupt cycle, and then at the end of this you also set R to 0. So that, I mean, kind of obviously, because you don't want R to be 1, like, because then you just like run again and again into the same thing, and that doesn't make sense, right? Yeah, so actually that's not quite correct. What I should be saying is, so if R is 1, okay, actually that is correct. Like if R is 1, it will just directly go to the 0th location every single time. That doesn't make sense. Yeah, but another reason this should not happen is, like, say you are running these instructions, the one that are for the interrupt, and then suddenly the user interrupts it again. Then at that point, whatever is this value, whatever is the address of this thing, so program counter is like here, whatever is this address, that's what will be sent to the to this location, and so the previous data is trashed or overwritten. And that's kind of a problem, because now this thing is stuck in this process where, okay, it goes there, it reads all of this, and then it goes to, oh, what is this address? Oh, this is this address. It goes there, and then it does the same thing. So it's stupid, basically. That's what I'm saying. So don't do this thing. Don't let the user interrupt when it's running the code for the interrupt. And so for that to happen, you also set the enable to interrupt to 0, right? Okay, so that's enough of a description. Now I think we can like really start drawing the flowchart. Right, cool. You know, why am I even deleting this stuff? So let's just draw the flowchart. So first we just have to start. So just some elements that will be in the flowchart. A box that represents a state. This thing that represents a condition. So you know whether the variable is 1 or 0, or whether the condition is true or not. This thing is an operation. So this is done during the transition between states, but this will not be like used in the flowchart. So like never mind that. And yeah, actually that's pretty much it. These are the only rules. So state is, you know, something that is how do I say this thing? Oh wow, this is kind of hard to explain without explaining FSMs. But there are these things called FSMs, which use states, and so in this flowchart this corresponds to a state. But for this particular circuit, you don't have that directly, although you do have it in some way. The SC thing actually just generates states, you could say that. I don't know, it's slightly different from a normal FSM. But yeah, so what I was saying is that, okay, these things will just be like, so these are related to the control, sorry, the timing controls, right? So like T0, T1, so on. At the same time, at what condition are you doing the operations? As in, if you have reached the T0 time, but you don't have like R equal to 1 or whatever, some other conditions. So depending on those conditions, you will do different things. Okay, so let's just start drawing it. So first you have the start. So just when you run the computer, you start its power and all that. Yeah, so there's this S flag, and I know another flag, which basically tells the computer to stop whenever it's set to 1. So we'll set that to 0. Alright, the program counter will be set to the first thing. So PC will be set to, I'm calling it the 0th location, but I should just be calling it the initial location where it's supposed to be. So that will be some fixed thing. Alright, so you can think of it as a reset thing. So basically just set reset equal to 0, so reset equal to 1, and then whatever the computer is supposed to be at the reset stage, it does that. Alright, yes, I guess. So you program it, you reset it, and then stuff happens. Alright, you could also reset the whole memory, but I think that's a different scenario. This is a different reset. It's just starting the computer. You want it to have some certain things before it starts running the program. Okay, so these two are there. Just gonna call it the start state, like instead of doing all of that. Okay, so now the first thing it checks is if R is 0 or 1. So if it's 1, it runs an interrupt cycle. Alright, so the first stage, I think I already told you what it does, right? Okay, so let's just start it. So in the interrupt cycle, the first thing it does is what's the first thing it does? It wants to send it to that location, right? Yes. Okay, so it has to store the value of the program counter somewhere, because we want to change program counter to 0 eventually, or 1 basically. So we have to set it to 0 and then to 1, because there's no way of putting random numbers with the program counter like easily. So we'll just set PC to be 0, right? But we also set this thing. So, or okay, let's not set it to be 0 exactly. Well, never mind. I don't know if this is correct. Yeah, I don't think this is correct. So you can't clear the program counter at the same time be sending its value to something else. So instead, you take the temporary register and then you give it the program counter's value. All right. So this is state t0. Okay, cool. And also at the same time, you have r equal to 1. Cool. So now in this temp register, you have the thing. All right. You also set the ARR thing, so you have to do that as well. So you do this stuff. At the same time, you also do AR equal to 0. So just clear AR basically. So once again, a single clock cycle is all it takes. So now AR is 0. Cool. Now what you can do is set PC to 0 basically, and then eventually we'll like increment it, but whatever. And also the AR, right? So whatever was the value stored in the TR thing, you can set that inside the memory. So MAR is TR. Okay, so this is state T1R basically. In the next case, what you is, what is I going to say? Right, so MAR is TR, that's giving it a value. Now you want the program counter to be at 1 basically, so just PC so just increment this thing, right? At the same time, now it's in the loop, right? So you have to disable the what do we call it, the interrupt, so the enable interrupt, right? So yeah, so you have to disable that. You also have to make r equal to 0, because otherwise it will just be stuck. Doesn't make sense, right? So that's like precautionary measure or whatever. You also have to make the SC thing equal to 0, because obviously. So what SC equal to 0 does is that after this state, you go back to the T0 state essentially. Alright, so that's just the instruction cycle. And let's start drawing the, sorry, this is the interrupt cycle. Let's start drawing the instruction cycles. There are like multiple of them actually. So yeah, okay. So first we have to fetch, right? So how do you fetch? Whatever is in the program counter, just put that in the AR thing. By the way, so AR is the only thing that you can use to get some stuff from them. Okay, this I should have drawn actually. Happens sometimes, but yeah, you do have this stuff. Sorry. Right, so AR is the only thing that you can actually use to get stuff from the memory. So yeah, it's kind of important. So this is one thing that you have to do. Whatever is in program counter, just put that, and then increment the program counter. Alright. Yeah. Wait, is this correct to be doing that? Like, I think it is. Yeah, I think it is. We could have done this later as well, right? Yeah, I mean, we can do the incrementing later, I think. We'll decide what to do. So now that you have the value of the program counter into the AR thing, so you can use this to get the instruction register value. Okay, you know what? In the second step, we'll do the program counter incrementation. Cool. You know what? I'm gonna draw it slightly better. So increment the program counter, at the same time whatever is in, draw it slightly bigger. So inside of the instruction register, you have to put this stuff. And so notice that the decoder thing is combinatorial, it's combinational, so it's gonna do its job like immediately. You don't even have to wait for a clock cycle. So yeah, don't you like just don't worry about it. Now the only thing remaining is to basically put whatever was the address inside of the instruction into our AR thing, because we want to be using that later on. So instruction, and then just have 0 till 11, I think, or 11 down to 0, right? Yeah, you do that. Yes, yeah, I guess that's correct. I think so. I think this is correct. Anything else I'm missing? No, this must be it, right? The decoder stuff is like happening automatically. I'm not going to write that. Okay, in the next thing, what you do is you use the D7 value. So remember what D was. D is somewhere over, yeah, here. So the operation basically that is signified by 3 bits, you can decode that into D0, D1 all the way till D7. So D7 would basically be corresponding to 111. So whenever you have this thing, it's a special code. So whenever it's a 111, you have a different operation than just what it would be if it was not that. And if it was not that, I'll do that scenario first. So if it's 0, in that case it's not that. Then you go to this I thing, which I told you was for direct or indirect you know referencing, right? So in case of the indirect referencing, okay, so once again 0 or 1. So if it's a 0 thing, then you basically do nothing, right? And you just proceed. But if it's 1, in that case, what you have to do is what was I going to say? Yeah, right. You have to get whatever is the address, so whatever is the data at the address in AR into AR basically. So why are we doing this? So the thing is that MAR, so that the data that AR is referring to, that's not the actual data anymore. Instead, it's a reference to the actual data, and so it's indirect way of referencing. So in the direct reference, you are referencing the data itself. In indirect referencing, you are referencing a reference to the data, if that makes any sense. All right. So once this happens, you can combine your path, and then you just have to do one single thing, which is the operation. So this is T3, yeah, corresponding to whatever path you have taken. So it's like not R, not D7, and maybe like I, that would be this thing, or not I, that would be this thing. Never mind all that. Okay, so now you look for the you look for which operation we are trying to do. So you have these D things, right? D0, D1, so on. So D7 is like 0, so you just have 6 options, 7 options remaining. And so for each of these 7 things, you will have certain operations that you can do. So first you have the D0 thing. In this case, you just AND whatever is in the accumulator and in the address basically. So AR refers, so MAR basically is some data, right? AR refers to that data. You get the data and then you AND it with the accumulator and put that stuff in the accumulator, and that's what this D0 operation is. So it's called the AND operation kind of, obviously. But what you do is, so I think draw this slightly bigger or something, I don't know. That was not a good idea. Okay, so this will be okay. So for the AND operation, first you gotta fetch stuff. So in your data register, which is the register that is connected to the accumulator, you input MAR, right? Yeah, and then you do A is, so basically accumulator, that's just the accumulator plus the data register. We are running out of space, aren't we? I'll draw that slightly smaller. Okay, I'm just gonna say that this is and. Yeah, this will be better. Okay, cool. I just want to like fit all of this in one page because it will look like a good summary basically. So this is just given AC plus DR, and you also do this stuff. Actually, you just do this. Oh, you also do SC is 0. So what SC equal to 0 does is that it sends it back to T0, that is the starting point. All right. Then you could have D1 being equal to 1. This is 1, this thing is 0 obviously. In which case, once again you do the same thing, you fetch the value of the data, and this thing is called the add operation. So it's kind of obvious what we're going to do. Oh, this was the add operation, sorry. This should be AND over there. So logical AND, yeah, bitwise basically. And this is the arithmetic add basically. Cool. And so now you have a D2. So once again from the, so you get this, this is actually getting really burdensome to draw, isn't it? Copy this, I'm just gonna keep pasting that stuff. Alright, so if it's D2, in that case, so it's and add, then it's load A. So whatever is the data, you just load the accumulator with it. So just the accumulator and then the data register. Oh, actually you don't have, you can sort of skip this whole thing and just do it in one single operation, so you don't have to do two cycles, like, yeah. I think that's correct, right? Is it? Hey, wait a second. You can't just give the accumulator any random thing. Oh yeah, okay. So you actually have to do it with 2 cycles. Right, I kind of forgot that. So the problem with this, what I was going to do was basically accumulator given MAR. This is wrong because the accumulator does not have a direct access to the bus. So it cannot load from the bus directly. Instead, you have to, whatever is the value of the ALU, you have to give it that. And so the ALU like really just depends on the DR thing and the AC. Like forget the input register thing. So in that case, you actually have to access DR. Otherwise, you cannot send anything to the accumulator. So this will be wrong. Instead, what you have to do is AC gets the value of DR, and then obviously SC is 0. Cool. And then you have D3. So once again the same thing. I'm gonna paste it. Alright. So this was the LDA. Now you will have storing. Oh, so this is something that you can actually do with just a single operation. So single clock cycle. So what will happen is, inside of the memory, you just put the accumulator's value. Yeah, it's that easy. So just store basically. Now you have some branch instructions. So this is 0, 1. So first branch instruction is called BUN. So branch unconditionally. It's at D4. So yeah. So whatever is the AR value, the address, you just want to branch to that. Like you want your program counter to go to that. That's kind of the only thing that you're doing. No saving, storing the value of the program counter, nothing. Just go to there. Like, yeah. So it just happens in a single cycle, basically. Oh, you also have to have SC equal to 0 over there. Yeah, that's kind of important. The SC being set to 0, because otherwise it will never go to T0. This is yeah. I mean, it will, but it will like take multiple cycles, and that doesn't make sense. So yeah. And it was like it might just go to something that is not correct. Like if it was supposed to stop at T5, it went to T7, and well, T7 is part of some other operation. Like it messes up, right? So yeah, D4 is the branch unconditional operation, which is so whatever is in the AR thing, just put that in the PC. Easy. Uh, yeah. So by the way, just a thing. The PC doesn't hold the value of the current operations address. Instead, it holds the value of the next operations address. Like while we are doing all of this. So just keep that in mind. So whenever you go back, you will actually get whatever is the value of PC after this clock cycle, after this operation, into the AR thing. So don't worry. You don't think like, oh, it's gonna increment it. No, it won't. It won't. It will increment it just so that you can keep track of what's the next operation to do. And so yeah, you just do this thing and S equal to 0. Right, that's D4. Let's go to D5. So D5 is branch and save, basically. BAS or BSA, I think it's called. Yeah, I think it's called BSA. Branch save. No, wait, branch and save. Huh. I don't remember the name, but it's something like that. So I'm just gonna draw this. So the reason I'm not looking this up is because this is more like a test for me rather than an explanation. Also explains why I'm drawing this really boring thing when nobody wants to hear it. But yeah, okay. So branch and save. Okay, let me first explain what this thing really does. So you know what a function is, right? What a function call is. For anybody who has ever done a bit of programming, you would know what a function is. So basically, what happens is your program counter is at some address, right? And over here you have some block of code where at this line. So after this you have some lines basically, and it does stuff. And so what a function does is it sort of stores the value of this address at some location, and it just happens to be the line before the program starts for the function in this implementation. And then once the program has run, it just sort of goes back to that address, and it goes back by basically doing an indirect referencing. And so this is basically a function call. What happens is whatever is in your program counter, you send that you just send that to some temporary register, because it wants to be storing that, right? Yeah, wait a second. Hey, that doesn't work. Oh, okay, you send it to the MAR thing. Sorry, I kind of forgot this. So you send it to MAR. Okay, what we are doing is AR is the location of this 0th line, if you will. I don't know. So the line before the function block, right? And so you want to store your program counter's value at that address, and then you want your program counter to come here. How do you make it come over there? You just increment the array, sorry, the address, right? So whatever was this address, you increment it to get to this thing. And don't worry, both of these can happen simultaneously. Do not worry at all. Yeah, this is still weird. Sometimes it does feel weird, but this this can actually happen simultaneously. Don't worry. And then what you do is, in the next step, so this is step 1. In the next step, you set the program counter to be array. Yeah, just AR. And then obviously S equal to 0. Okay, yeah, that's the thing. So yes, these can happen simultaneously. The reason this happens is D flip-flops, or more like master slave D flip-flops. Just think about it, what's exactly happening, and you'll realize yes, this is actually very much, it does happen. Yeah. Okay, how do I exactly explain what's going on? So I think, yeah, this will be doable. So you remember how a counter works, right? A synchronous counter. So you just have these D flip-flops. It has some values coming out of it, whatever. And every D flip-flop is actually 2 D flip-flops. So you have something that only accepts stuff at the negative clock edge, and something that transmits stuff at the positive clock edge, right? I'm just gonna shade this as, black basically, so that you can think of it as, okay, so this part will store the value at negative clock edge, right? So a counter basically has the input as, some logic function of all of these guys, and yeah, it just sends the value into this thing, right? It actually like toggle flip-flops, but like that also just D flip-flops in the end, so never mind all that. Just think of it, everything just being D flip-flops in the end. So it actually, then in that case you also have to take this into account, but whatever. The point is, all of this like happens synchronously, so you have like the same clock for every single thing. And so what happens is, you have these outputs of the logic. All of these are suddenly stored into this negative part of the flip-flop, like everywhere for all flip-flops in the counter, but these are unchanged, right? And simultaneously what's also happening is that these outputs are going somewhere, where these are going into the, like, what was I going to say? Yeah, these are going to the memory. So this is the AR thing, right? So these are not changed yet, and these are going to the memory, right? And so whatever is corresponding, like a word for that is not changing, like as the negative edge is passing, that has not changed. But what's actually happening is, this data is actually like, so since it's a negative edge, yeah, this data is like being spit out in the program counter. So let's just think of it as the negative part of all the flip-flops. So that is in fact taking the input inside in the negative clock edge, but yeah, it's not changing its output, like the flip-flops output, if that makes any sense. Yeah, but as soon as you get the positive edge, this part actually moves over there, and so now the array thing is, so the AR thing is incremented. Your word also changes, but this has moved over there, so like now it doesn't matter because the PC is got the correct value corresponding to the unincremented AR. Okay, that was enough of an explanation. Yeah, so like both of these can happen at the same time. Once again, to recap, what did I say? MAR gets the PC value, and you increment AR. Oh, okay, it was the opposite way around, right? Never mind all that. You can also say that, okay, the word gets the value of the PC and all that. So you get it, right? And then PC gets the AR value. Cool. So these are our two steps. I'm just gonna draw that. So the first step is obviously just this. And in the second step, we just have PC getting the value of AR and SC is 0. Alright. That's D5, the last memory based operation. It's called ISZ and it has 3 states. It's weird, I know. So what is ISZ? ISZ is basically like increment the value of MAR, right, whatever data you're referencing to, and then if that incremented value is 0, skip the next operation. So by the way, the next operation is already in the program, so next operation's address is already in the program counter, so we just increment that by 1, so that like whatever next operation was, you go to the next of that, right? So you're skipping the operation. So this is going to be straightforward to draw. So first what you do is you just put this into the DR register, right, the MAR thing. Then you increment this value, so just DR plus plus, right? And then you put that back basically. But at the same time you also do a conditional, so I should be drawing this somewhere else, or maybe I should draw this somewhere else. Yes, I know, this is, I just wish I had a bigger screen. I guess buying a tablet isn't that bad, huh? Look at me, all the consumerism talking. But yeah, so just MAR is this thing. Uh, so I put that back, but at the same time, you also have to just sort of. So you have incremented, put it back, but at the same time, so the DR value is actually holding the incremented value. So if it's 0, so if DR is 0, then you have to increment the program counter, and obviously s equal to 0. That has to happen. Oh yeah, so that does the does this part basically, and I don't think I'll be having enough space to draw the other part, but let me try. Oh damn, this is going to be really hard, isn't that right? Okay, so what happens if d7 is 1? So if d7 is 1, you have two sorts of instructions once again, and they are based on the I value. So at this point, this I is not indirect or direct or anything like that. Instead, it's like input output and uh, RRI operations. So RRI are register reference operations. I just kind of told you. So yeah, uh, this is going to be tough, isn't it? So if this is 0 and if this is 1, so if this is 1, it's input operations. If this is 0, it's RRI operations. Okay, and so how do you decide which operation we are doing? So the OP code operation, the instruction code that looks like this now. The first four bits are basically either 0 1 1 1 or 1 1 1 1, whatever, and the other stuff, these can be thought of as the decoded values um, of potentially up to 7 classes of operations. So it could be like this is 1 0 0 0 0 so on, or this is 0 1 0 0 or something like that. So let's just call this bit as B11, B10 and so on, all the way till B0, right? So this is, by the way, the instruction register we're talking about, and then depending on the values of these will like decide what operation to do. All right, so first if you have B11, then you're going to clear A. So instead of like drawing all of this stuff, which is actually going to be really hard actually, I'll just mention what is going to happen. So clear A is basically like just clear so just A equal to 0. Wait, can I actually sort of draw this? I don't know, looks like a hard task. Yeah, it does look like a hard task. Let's actually try. Like, what's the worst that will happen? I'm gonna put this as 1. Nah, this is actually better as 0, right? And then the 1 stuff I'll like do it later. I'm just gonna do this first. Okay, so I'll draw it in the opposite direction. So B11 is just clear A. So just do A is, so accumulator is 0, and SC is also 0. Obviously SC is 0 all the time. Then B10, this thing is clear E, so obviously E is 0 and SC is 0. I can decrease this a bit. Alright, then you have B9, which is complement A. So now AC just becomes AC complement. So this is just done with the ALU, like directly. The ALU has capability to be doing this stuff, so like don't worry. In a single clock cycle, that is. B8 is complement E. So all of these are like all of these RRA operations are done in single clock cycles. Okay, so just E becomes negative of E, and then SC is 0. Then B7, which is circulate to right. This is slightly complicated, like just a bit. So accumulator gets the right shift of the accumulator. The 15th bit of this thing that gets the value of what is it called, the E thing. So that's what we input that, and then the E thing gets AC0. So just know that all of these happen simultaneously once again. Like in the negative edge, all the inputs are there, in the positive edge, like they are propagated to the positive part, if that makes any sense. Yeah. So that's B7. Circulate to the right. Then you have B6, circulate to the left. Once again the same thing as that, but now AC gets shift left of AC. AC 0 gets E, and E gets AC 15. I also have to have the SC equal to 0, but I'm just gonna assume that that thing is there. B5, that's the increment operation, so it's just AC plus plus, nothing much. Okay, then B4, this is getting really weird, isn't it? So these are the skip operations now. So you skip, not K, sorry, don't have K. You skip on the case when your accumulator is positive. So you know, if AC 15 basically, in that case you say that your program counter is incremented. Then you have a skip at negative, and you have a skip at 0. So skip at negative is actually exactly like this, except you have, so this actually has to be 0. So if not, basically, then that's a positive or non-negative number, and this would just be the thing, right? Skip at 0 is slightly different, so it has to have, if AC is completely 0, like all bits of AC are 0, in that case increment PC. And you have SZE, which is skip at 0 for the E value. So if you know E is 0, in that case, so then PC plus plus. I mean, this is like really boring, but I am going to draw all of this in the exam, so just bear with me. Not in this much of detail, and I won't like be explaining all of this, but yeah, all of this is in fact important. And then B2, I think this was it, right? B11, B10, B9, all the way to did I? Oh yeah, okay, so I think that's the mistake. So B4, B3, this would be B2. This is B1, this is B0. So B0 is just the halt operation. So you just set S to B0, S to B1. And you don't even like care about SC at this point. Like once S is 1, just stop. Right. So these are all the operations when you have RRA operations basically. And then finally you have the input-output operations. That's a really bad line. Okay, slightly better, but whatever. So I should make this bigger, I think. Yeah, that's much better. Okay, so now we're going to these last sort of operations. I want to kill something. What is wrong? Like, why is this happening? I just did that, and okay, it just vanishes. Amazing. Okay, so we are going to the final sort of operations, which are, yes, these are the operations. I don't like this, but whatever. So first operation is obviously the input. This is at B11. It's called input, and it's pretty obvious what we're going to do. We're just going to put whatever is in the input register to the accumulator. Or more like whatever is the input to the lower bits of the accumulator. But yeah, and obviously s equal to 0. So that's pretty easy. In B10, it's output. yeah, yeah, this is, I just really don't want to be doing this. So whatever is in accumulator, you put that in the out register. The way this happens is through the memory bus, obviously, but I'm just gonna like draw it directly. So out register gets the value of AC, SC0, whatever. Yes. Then I think there are like a bunch of skip statements. Is that correct? Yes. And then you have some enable and all that stuff. Okay, so I'm gonna try doing that. So maybe it's B9. I have no idea whether or not it's this thing, but let's do it. So skip at whether the FGI thing is high. So if FGI, in that case, just make program counter plus plus. Right, that's this thing. And you have B8 SKO. If FGO, yes, then you have B7, which is so interrupt, just make interrupt on or off. So I on, that basically like makes the enable for interrupt on. And then obviously you have the off statement as well. No, this wasn't a good idea. Okay, I'm just going to cry if this thing continues. Oh god, why is this so messed up? Okay, I think this works. Well, never mind. So finally just have this B8, which is IOF. So that's just making the enable interrupt off. And there you go, that's all the instructions. I'm hoping these are in the correct order and all. But let's try seeing what's the correct thing. Okay. So the start state is 1 second, just SC0 and all. So instead of that, I should just really say that, S is 0, SC0. And your program counter is at the initial state. Yes, that's the start state. Fine. I think ISZ has 3. Yeah, okay, it does have 3 and all. Alright, so far it's good. Okay, yeah, so the input output operations do happen at I equal to 1 and D7 equal to 1, and And so you have these operations: INP input, OUT output, SKI SKO, ION and IOF. So pretty obvious, right? The RRI instructions on the other hand, they're slightly complicated. Yeah, also you have this sort of like always existent boolean logic that your R will be set to 1. So like you have all these instructions, but the thing is I didn't mention one thing. At the every last box in your instruction, um, so like whenever you set SC equal to 0, you also have to set this, not the last box, but like every box which is not these boxes, right? So everything below that. So if it's not T0 or T1, I should draw bars, not these prime things. So if it's not T0 or T1 or T2, so if it's none of these, in that case what you have to do is, like, if you have enabled your interrupt and your FGO or FGI are there, right, in that case you probably should interrupt. So in these cases you just set R equal to 1, right? So this happens for like every single box after this, basically, like, yeah. So you can think of this R as being just another sort of register, just a single bit register, which is like, so it's 1 if this happens, or maybe it's just one flip-flop, like a JK flip-flop or something. And so you will just set J to this will be like 1 0 if this happens, otherwise something like that. Okay, probably I should be changing this a bit. How should I explain this though? So the thing is that the R should be 0 only whenever this is triggered. So whenever you have this, you set it to 1, like sort of indefinitely, like it just is 1 for most. Yeah. It's hard to explain. It's really hard to explain like this. A toggle sort of, yeah, I mean, if you are in this thing, then what probably happens is that R is 0. In that case you just gotta toggle the thing, right? So I guess we'll just be toggling this. So think of it as a toggle flip-flop, and the value, so output value is R, right? This is the Q thing basically, and your toggle input is basically this stuff, T0, T1, T2, which of them barred, enable input, sorry, interrupt, FGO plus FGI, but all of this only happens like if your R is 0, so probably you should also have R 0 or something. Heck, why am I clearing so much? Alright, plus so other case where you can probably toggle it is if you have reached this instruction cycle branch. So basically, like, this is T2R, right? Yeah. So it's like R was 1 in that case. So whenever like T2 happened, at that point you gotta flip this. Yeah, so if it's T2 you can flip it, or if it's not, in that case you also have to have, like, it's not T0 or T1, and this must be there so that you can flip it. Oh, and obviously you gotta have the enable. Actually, you know what, that enable will be there in any case, so it makes sense. So that will be the input to the R T flip-flop, I think. I don't know. They never really talked about like what the actual thing is for R. Okay. Yeah, these small things, like, they never really talked about. But anyway, let's just sort of make sure we are going correct. So let's go to this part, the instructions, the interrupt cycle. So AR gets 0, TR gets PC, that's okay. Then MAR gets TR, PC gets 0, that's okay. PC gets PC plus 1, so PC incremented, yes. The enable, oh, so they're calling it IEN and not ENI. So I'm gonna call it IEN as well. Or you know what, whatever, I'm calling it EN, I'm gonna call it ENI. So enable interrupt, interrupt enable, make that 0. R will be 0, SC will be 0. So that part is correct. Let's go to this part now. So AR gets PC, fine. IR gets MAR, PC is incremented, yes, that's okay. And then AR gets this stuff, that's also okay. Alright, what about this? So if it's indirect, then you do AR, it's MAR and all that stuff. Otherwise nothing, and then you execute these instructions. I kind of have confidence that these will be correct. Practicing this for kind of a bit now, but yeah. Let's go to these, then RRI operations. So register reference operations, yeah. All of these just happen single clock cycle, so cool. So it's clear A, clear E, clear complement A, complement E, circulate to the right, to the left, increment, yes, skip at positive, skip at negative, skip at 0, then skip at 0 for E, and then halt. So the correct things, and I don't want to be looking at these things because these are most probably correct. Fine. Okay, then you have the input operations, fine. So input output, yeah, okay. So what happens at the INP thing? Oh, I missed one small thing, and that is the flags. So you also have to set the flags over here. Okay, so what happened? INP is like you take the input. So once you take the input, you have to make sure that like the flag is 0. So flag for input will be 0 at that point. Over here as well, once you take the output, the flag for output has to be 0. Wait, no. What happens when you do this? Wait, what? Oh yeah, okay, it has to be 0 actually. Because just think about it, like, yeah, you have transmitted what was in the accumulator to the output register, but it hasn't like gone to the device yet. So it has to be 0, right? Yeah. Otherwise it's all okay. So yes, apart from that little bit of a mistake. Cool. Yeah, it's okay, it's completely okay. Fine. So this diagram basically tells us everything, like what's gonna happen at what point. And finally, let's go to the accumulator design, which is like kind of a small thing, but yeah. So you have this accumulator, and it takes stuff from the ALU, right? When do you want to load the accumulator? That's the question. This is a load for that. Yeah, so like figure out all the cases when you will be loading the accumulator, right? So let's see, for all of these things, for the AND case, so I'm gonna label it, right? This is T3, this is T4, this will be T5. So the accumulator is loaded in, so I'm gonna use a red thing now. It's in T5 and in T5 over here as well for D1, and over here as well for LDA. This, yeah, accumulator is not loaded over there. Nope, not loaded over there. Nothing happened over there. Nothing happened over there. Nope, no accumulator. Fine. So that's okay. Let's see. Over here, yes. So you have to figure out what accumulator. Wait, okay. It's not being loaded, but rather it's being cleared at that point. Could it be that I can set it to 0 or something? I don't know. I actually don't know. But I think I'm gonna include that as well. Okay. This is certainly something that you need from the ALU. This, yes. This, yes. Yes. Wait, but you just have the increment, so you can directly increment. So why even do this? I don't know. I really just don't know. Wait, so can't you just increment using the ALU? Why do you need... Uh, yeah, that's a good question. I'm just gonna look that up. See. Yeah, I mean, shouldn't it make sense? Like, if you have a whole ALU, why should your register ever have the facility to increment? It can always increment, right? Oh, but it does. It does have an increment facility. I don't know. It also has a clear facility. Well, this doesn't make sense. So I guess we should not be having these things. These will be in the increment and clear scenario. So I'll just say, like, whenever you're doing AC being 0, that stuff will be in the... Yeah, so when is AC 0? Yes, over here it's 0. So I'm gonna mark that as blue instead. Right. This is a clear facility usage. Okay. Increment is also a usage where, you know, they're not using the ALU, in fact. What about this one? Well, okay, the accumulator is not actually loaded in the first place. Nope, 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 nope. Let's check those as well. Yes, you did use the ALU, you used the ALU, you used the ALU. Yes, all of this is okay. So the only cases, and you know, just for the sake of it, I'm actually gonna draw, so like write down the whole thing, like all the control signals that were involved in the state. So this is R is 0, so not R, not D7, and well, the I thing doesn't really matter, so not R, not D7. Yes, this is the same thing, just have, so also this stuff, so like D0. I mean, okay, if D7 is not, then obviously this is gonna happen, so I'm just gonna say D0 over there. This will be D5, not R, and D1. Yes. I'm just wondering if this... Yeah, okay, it will reach T5 in other cases as well. So you can't just do it like that. Like, this is also just T5, by the way. Okay, what about this one? This T5, not R, and D2. Yes. Let's go at this now. So here your R is once again not R, but your D7 is 1. Okay. So just have T5, D7, not R, and B9. Oh, not this one, sorry. This as well, just T5, D7, not R, B7, T5, D7, not R, and then B6. Yes. So these are the things that will be used in the load operation for the accumulator. And so you just have a big OR, and then it has a bunch of ANDs. So this will be for the... Let's start. So the complement A, circulate right, and circulate left. I wish I had like these things memorized, like what is the code for this, what's the code for that, but I don't. So I'll have to look it up so many times, and that's why I memorized the flow chart rather than memorizing each of the constituent like codes, because that would be a nightmare. So it's 9, 7, and 6. So it's supposed to be T5, D7, not R, and this is B9, this is B7 and B6. Cool. So this quantity is like common to each of these, so I'm just gonna call it something. call it R. So it's just the AND of these guys, D5, D7, and not R. Alright, and you just have these extra things, B9, this thing is B7, this thing is B6. I think so. Yes, that's the way it is. And so all of these guys go into the big OR gate. Right. We also have the other stuff. Oh, you don't actually draw it like that now. Yeah, this connection is not supposed to be there. It's only limited to that. Okay, the next thing you have is this. So T5 and not R is actually still common. Let's call that something. Call that P probably is not a good idea, so call it B or something. So it's an AND of T5 not R and D0. Right? Yes, I know T5 not R is common. You can make just a logic gate for that and then do stuff, but whatever. Be a little lazy. So what is this? D0, D1, D2. Cool. So it's just and add and load A. And that's the stuff that goes into this OR. Right. And that's the load operation. You also have the clear operation. And so you only have to clear at one particular case, which is clear A. Yes, which is B11. So it's T5, D7, not R, but B11. So it's just whatever this R value is. I'm gonna take it like that and put it over there. Oh, but I have to put a AND gate over there, right? So this, at the same time, you also have to have B11. Yeah. Well, that makes sense. And then for the increment, it's B5. So it's the same as that, and then you also have B5. That's the accumulator. Yeah, that's how you design a circuit. Fine, let's just look at the thing. Let's see if it's correct. I guess the design was somewhere over there. Oh yeah, right. Okay, cool. So for the increment, oh, it's actually called INR and not INC, but who cares? Yeah, so the increment pin has obviously the INC, which is B5, and it's having this R thing. So what's R, by the way? Did they ever write it? I don't think they did. Oh, they did. It's D7, not I, and T3, which is... Hey, that's not quite what I wrote. Oh yeah, okay, I missed this one thing. This I. I don't like this. Okay, so in the case of the... So in these cases, we don't really care about I, because it doesn't matter if you're doing it directly, indirectly, whatever the hell. Yeah, but in this case, you do. So it's not just this, you also have to have a not I, because otherwise you're going for some input-output thing, which actually does use accumulators sometimes, right? Yeah, okay, I think I messed up once again, because apparently this is there. Wow, I don't like this. This is B11. Fine. Anything else? No, this is the only one which is its accumulator. That's B11 and not of this. Okay. You also have to have that now. Yeah, right. So it's B11 and all of that. I, D5, D7. Yeah. put that into this thing as well. Fine. Cool. This thing is called P, by the way, the T5 T7 thing, but like never mind that. So it's P and B11, that's the input. So that also goes there, right? Makes sense. So yeah, they defined R as D7, not I, and D3. Wait, what? D3. I wrote it as T5. Why did I wrote it as T5? Oh, it clearly is T3. I mean, think about it. This is T0, T1, T2. And this should be T3, right? Yes. Oh, because over here it should be T3, T3. That would be T4, that would be T5. And it's almost never going to be in the T4 case. So that's why I wrote it like that, huh? So all of these should be T3, not this. This is in T3. Okay, this is actually T3, right? Yeah. This as well. No, wait, okay, that's actually correct. These are the ALU cases. And this is T3. Cool. Fine, okay, that makes sense, I think. That's R. What is P? They didn't define P, I think. But they did use the P thing. Yeah, well, they didn't. But never mind, we know that P is just going to be D7, I, T3. Which is, yeah, I mean, we are using that, obviously. Okay. So it's the P and B11 case, which is basically your INPR, input register. So I was calling it input register, but basically just the input operation. Yes. So it's gonna load the input register instead. That's kind of what they should say. Okay, so let's just go over this. So first you have the AND operation, which is there, yes. Then you have the add, you have the DR, which is basically like the load operation. So it's gonna load DR in case of LDA, right? You have the complement, yeah. You have the circulate right, so that is where it loads. Circulate left, yes. So this is there. I'm just gonna like give this check. Yes, okay, that's there. And then increment and clear. So the clear is, oh no, the clear is for this thing. Okay, cool. Wait, so the increment thing is for, wait, what? Okay, yeah, okay, let's do it again. So and, yes, add, yes, load the input register thing. So that's the input operation. The complement, the shift right, shift left. Okay, cool. So you have like 1, 2, 3, 4, 5, 6, 7 operations where you need to have this. And then finally you also have the increment and clear things, which is for the INC operation. And clear, so it's just literally called as clear operation. So yeah, that's how you do the accumulator design thing. Fine. Okay, so that's just like, yeah, so this is like the input to your accumulator. How do you build the accumulator, right? Yeah, I mean, given these inputs, so like whatever is the thing from this OR gate, from these two gates, what was I going to do though? I kind of forgot what I was going to do. Oh yeah, I completely forgot. Yes. Wow, I don't remember stuff. But I guess this must be it. Yeah, I mean the ALU thing should probably be giving us whatever we want, so it's okay. Yeah, I guess so. We should stop for now, and I'll do another video soon. So see you guys in the next video. Bye.